Now let us proceed to next speaker. Next is Kim Plofker. She received her PhD at Brown University, as I said, and has been a visiting researcher on the history of mathematical sciences at many institutions, including the Max Planck Institute in Berlin and the Chennai Mathematical Institute. She is currently assistant professor of mathematics at Union College in New York. So please.
Well, while they're getting the slides set up, I would just like to say thank you to the organizers for the honor and the pleasure of being included in this conference, which is one of the best conferences I've been to, which is largely due to the efforts of the wonderful volunteers. I don't think I've ever been so well taken care of at a conference, and I will remember all of them very fondly, especially when I'm in the airport and have to carry my own bags. I'd also like to thank the previous and the following speaker for their very interesting and enlightening contributions as well, many of which have saved me the trouble of providing a lot of the background information. So let me begin. Could we change the amount of light, do you think? I think it's a little too bright on there. We've heard much of great interest today about both the Grahaganita and the Karanakutuhala, as well, of course, as many other works of Bhaskara. I'd like now to investigate some aspects of how the Siddhanta rules, specifically the calculation algorithms in the Ganitadhyaya of the Siddhantasiromani, have been transformed into the Karanakutuhala practical algorithms. The comparative size of the two works that you see here in the verse counts speaks for itself pretty much. You have many verses in each chapter of the Ganitadhyaya, or in almost every case, significantly more than in the Karana text. So that is the comprehensive variety and multiple approaches to astronomical problems in the Ganitadhyaya have been tightly focused into what's mostly a strictly linear sequence of calculations. And what this indicates is that every word counts. The tolerances are tight for performing the astronomical calculations that you need in this small amount of text. The content and organization have everywhere been very carefully chosen. And since every word counts in more contexts than one, I'm going to skip my first example here, and to give me more time for the main discussion. I'm going to look at chapter 3, the Triprashna of the Karanakutuhala, which deals with the time and locality, or direction, place, and time problems that we heard about earlier today and also yesterday in Professor Sriram's talk. Now, the rules in this chapter illustrate what I'm talking about with regard to the tightly focused sequence of computation. They assume knowledge for the user of only the solar longitude, lambda, for a given date and time, and the equinoctial noon shadow, which I'm calling here S0, for the local place, and the so-called half equation of daylight, omega, which is simply half the amount by which the length of daylight, differs from the equinoctial day of 12 hours or 15 gatikas. So knowing those, you compute in a very precise order various other astronomical quantities relating to these Triprashna issues regarding your appearance of the sky at your, or time at your own particular place. In particular, I'm focusing on the computations for the gnomon shadow S and its hypotenuse H for some given time, which, as you'll notice, is then followed by the computation of the solar declination delta. And previous speakers have spared me the task of much of the explanation of the basic trigonometry of the gnomonic or shadow triangles. So I'll just give the basic setup here. Of course, if the sun is at true local noon on the equinox, that is both on the meridian and the equator, then you will see a right triangle formed by the shadow it casts and the standard gnomon of 12 digits or ungulad, and the hypotenuse formed by the sun ray between the two. And this triangle will contain the angles phi, the latitude, local terrestrial latitude, and its complement phi bar. So let me just skip over the trivial similar triangles that result in this expression for the noon equinoctial hypotenuse, h sub naught, and move on to the general case of a noon hypotenuse. If the sun is on the meridian but not on the equator, then you have, and I'm only going to consider summer days in this discussion just for simplicity so I don't have to keep adding or subtracting. You get a triangle of the same sort, but it has different angles. So the takeaway from that is simply that a formula is produced for the noon hypotenuse, which is equal to the noon equinoctial hypotenuse, which is the user is presumed already to know or to be able to find, times some trigonometric function involving the latitude and the solar declination. So again, without going into details of the Sanskrit or of the trigonometry, I'll just point out this particular formula from the Ganitadhyaya, in which Bhaskara gives a specific rule for the arbitrary noon hypotenuse as a function of the equinoctial noon hypotenuse times the trigonometric radius divided by some divisor. And the case then, the noon hypotenuse is a special case of the arbitrary hypotenuse. In the Karanakutuhala, he also gives a formula for the noon hypotenuse as a function of the equinoctial noon hypotenuse, h0, but as you see, it's quite different in form. And I can't resist pointing out what I had not noticed before the discussion yesterday, his use of this term kahara, which here, of course, does not mean divided by 0, but it's short for kamadhyahara. He's speaking of the mid-heaven or noon divisor, which is part of what he uses to compose this rule. So I think I didn't notice it, but that's definitely got to be a deliberate pun on Bhaskara's part. Now, you see that although these two rules have a general similarity in structure, they are simply the noon equinoctial hypotenuse multiplied by some factor, they are mathematically very different. This approximation in the Karanakutuhala is not explicitly trigonometric, sort of an algebraic approach. Of course, these quantities, omega, the half equation of daylight, and the noon equinoctial shadow imply trigonometric relationships with the declination and local terrestrial latitude, but they're not explicitly stated, and as noted before, it means that the user does not have to actually use trigonometric functions in order to compute this noon hypotenuse. And this is a quite sophisticated approximation to a two-dimensional function of two-dimensional trigonometric function, and I thought it would be instructive to take a look at it and see how it behaves here. So I've shown a few graphs for separate values of the latitude phi of the noon hypotenuse h sub n in ungulas or digits versus the quadrant of northern declination from 0 to the maximum value of 24 degrees. And I show here the exact trigonometric formula from the Ganitadhyaya in blue and the Karanakutuhala approximation in red. And you can see that with some variation, depending on latitude, it is mostly quite a good approximation. Not perhaps one of Bhaskara's best, but within no more than a few parts of, less than a tenth of an ungula, so a few viungulas of difference from the exact version. And the most interesting thing about this, I think, is that unlike the vasanas we've been hearing about in the Siddhantasiromani and in other works, there is no vasana by Bhaskara on the Karanakutuhala formulas, and in fact, no yukti, no upapati, no attempt at a rationale for the nature, for the details of the formula in any commentator that I'm aware of, though I would very much like to look at the Persian commentary that Professor Ansari mentioned, and to find out if that attempts to tackle any of these. That is, the explanations we see by commentators tell you how to follow the steps of the algorithm, but not why we should assume that, to go back, this approximation in the Karana is approximately, adequately the same as this exact formula in the Ganitadhyaya. So I'd ask, how might Bhaskara have constructed this formula? Why would he have chosen to put it in this form? And I think the first thing to say in response to that is it even worth asking that question? I mean, let us be frank about this here. Bhaskara was a genius, and I am not. Is it reasonable to hope that I could get inside Bhaskara's head and understand what he was thinking about something that he deliberately chose not to explain? And, can I expect anything more than just indulging in a little random speculation about parallel construction that might be accurate and might not? Well, I think so. I hope to be able to convince you that, yes, it seems likely, partly because Bhaskara was a genius, but he was a very kind genius, which not all geniuses are. He worked very hard to make his techniques and rules clear and reliable for his users. And also in recent work in preparing an edition of the commentary on the Karanakutuhala by Ekanath, and originally inspired by work done by R.C. Gupta and Takao Hayashi on analyzing the algebraic approximation to the sine function given by the first Bhaskara. I have made a bit of a hobby of attempting to similarly analyze algebraic approximations of the Karanakutuhala as they attempt to represent trigonometric functions. And it seems to me that we can arguably, not provably, but plausibly, identify a sort of toolbox of methods that Bhaskaracharya and possibly other authors, astronomers before him, used for this sort of conversion from an exact trigonometric Siddhanta formula to a Karana approximation. That is, he seems to have repeatedly called on a certain set of elegant and simple and robust transformations that I hope can shed light on not only his work, but perhaps the whole tradition of development of a Karana or astronomical handbook text. So, if you are willing to accept provisionally that this might be worthwhile to explore, let's plunge in. All right, this is the task that we have set ourselves, how plausibly to suggest that Bhaskara might have gone from a trigonometrically exact formula on the left to the Karanakutuhala approximation for the noon shadow on the right. And it seems very likely that he would have begun with the divisor approximation. So if we just simplify a few terms here, then we get this denominator, and we consider that in the Karanakutuhala the radius is 120, so we can write it that way. And we note that when the radius is 120, then for small angles up to about angle 30 degrees, you can say that the sine of an angle is approximately equal to twice that angle in degrees. Of course, if the angle is 30, then the sine of 30 degrees is half of 120 or 60, so the approximation is exact. But for smaller angles, it's also reasonable. So this is, I'd suggest, one of Bhaskara's characteristic tools, namely linearizing, or just very simply and audaciously eliminating a trigonometric function and taking it to be some linear function instead. All right, that doesn't help us very much, but once we have done that, we remember that an angle in gatikas is just 1/6 of the same angle in degrees. So pulling out a factor of 12, we get this cosine delta times 12 times this 10 plus omega gatikas, and canceling that, we get this factor over 10 plus omega gatikas, which is in fact the Karanakutuhala divisor that we're looking for, got in what I would argue is a fairly transparent and natural way. All right, if we buy that, then we are left with the problem of converting this numerator approximation to what or this numerator term to what Bhaskara comes up with in the Karanakutuhala for the numerator. And clearly they're they look very different. But one thing I think gives us a clue is that we must, according to Bhaskara's sequence of computations, eliminate not only the trigonometric function, but the direct invocation of delta, the declination, because the user doesn't yet know delta in the Triprasna chapter. So how might we do that? Well, another of Bhaskara's tools that is frequently used is to squeeze the trigonometric function that he wants to eliminate into as small a term as possible. So if we divide through by cosine delta, we end up with 10 times 1 plus some remainder, which is now a ratio of trigonometric functions, the verse sine of delta over its cosine. And then if we perform some trivial substitutions from various other Triprasna triangles, with latitude triangles, which Bhaskara, of course, could have performed in his sleep, that I will not explain here, we get this expression. And if we do the same small angle approximation, conversion to gatikas, we end up with this. And that is, we're getting closer to the numerator that Bhaskara actually provides. Yes. So this is the formula that we're shooting for. Let's.
Last step, at the bottom of the slide.
Yes.
You have put in a factor of 12, no?
Yes. Because I have converted twice an angle in gatikas or twice an angle in degrees to an angle in gatikas.
But the next slide, there should be a factor of 10.
No, that's okay, because I have, I've canceled my 10 times 12 here with R, 120.
Okay.
Sorry about that. Yeah, I mean, it's, we can go over it in more detail, but I'm trying to keep on time here. So then again, with some trigonometrically trivial transformations, that's hard to say, I can rewrite this latitude term in terms of this expression, and taking omega as v-gatikas, I then cancel my 60 with my 120, and I get this as now my new numerator. You notice that the ratio of trigonometric functions involving delta is stubbornly persistent there. But if we look at how given the approximation so far behaves, it's not only fairly close to what Bhaskara has written, but is very close to the trigonometrically exact formula, but we still want to get rid of this factor versine delta over sine delta. And what I suggest Bhaskara did in this case was to use another of his standard tools, which is audacious substitution of one term for another with a linear factor. I'm going to cheat by just showing you a graphical representation instead of doing all the lengthy numerical comparisons. But if you consider what this factor, this first ratio, looks like compared to this second one that we want to get rid of, it's approximately 8 times that. And of course, if I have some factor W, which is about 8 times another factor V, then my product 2 times W times V is approximately 16 times V squared, which is 1/2 of the factor omega quantity squared. So, letting you think about that and moving right along, we say that if we are considering these 2 factors, we have what's become now a usable approximation with the trigonometric functions and the reference to the unknown declination delta eliminated, and we've produced this approximation with the square of half this known factor replacing 2 times the product of the known factor and the unknown factor. And what I would suggest for his last step that Bhaskara did was another thing that I think we've seen him do before, and I was delighted to see in Professor Sriram's talk yesterday that he mentions an example of it in the Ganitadhyaya as well. That is, you simply compare an approximation for one or a few very easy values of an angle to test. That is, if you take, thank you. Oh, that's more than I need. If you take a few easily computed values of the longitude and the declination, and you test for them this square of half, this omega over 10s naught, against what we derived from the trigonometric formula, 2 times this W factor times the V factor, you get this comparison for 30 degrees, 6/29 versus 1/4, 60 degrees, 36/55 times 81/100, 64/75 versus 256 2/25. Clearly, it's not a very good approximation, but I think it's that sort of comparison, especially in the case of lambda equals 60, would very readily suggest to Bhaskara that if he took a 1/6 away from this squared term, he'd get a much better approximation. It isn't perfect. As I say, it's not one of Bhaskara's best approximations, but it matches pretty well at many of the important points, and it is, in fact, exactly what the rule that Bhaskara gives in the Karanakutuhala prescribes that you should do with the known information. So, my argument will be, and feel free to object to it all you want, that this, or a procedure very similar to this, is what Bhaskara actually went through in order to convert a trigonometrically exact Siddhanta rule into a Karana approximation. And to complete my remarks, I'm just going to put up there my concluding remarks and draw attention only to a couple of them. First, that this is a very elegant and perhaps somewhat elaborate way of approaching this. Clearly, Bhaskara's approximations are artistic achievements mathematically and not just pragmatic simplifications. And certainly all the rules are constructed very carefully with regard to what the user already knows and what he doesn't. I'd also just note that an earlier tentative speculation that Bhaskara's use of 120 for the trigonometric radius perhaps hints at the influence of Islamic astronomy. This is not supported by this reconstruction of the hypotenuse formula, because clearly Bhaskara has reasons of his own for picking r equals 120. He might well have known that, or have encountered the fact at some point that Islamic trigonometric tables use sexagesimal values of the radius, but I think it was very much his own independent decision for his own reasons to use that in this text. And I'm going to stop there. Thank you very much.
Thank you, Tim, for very exciting paper. So, question then?
Yes.
Where did the delta disappear? Sorry.
The delta disappeared. Yes. The delta disappeared by simply saying this ratio of functions of delta is approximately equal to this ratio, or to 1/8 of this ratio of omega over 10 times S naught. I mean, that is, as I say, that's bold, but that's Bhaskara.
What is omega?
What?
What is omega?
Omega is the chara, the half equation of daylight.
Oh, chara.
Yes, yes.
So that there delta comes in some way.
Exactly.
Yeah.
Oh, yes, he definitely refers to, I'll have to step back
Chara,
a
yeah.
bit, but whoop, there it is.
Omega is chara. Okay.
Yeah, pratamakanda hrtam dalitam charam, that
Oh,
is,
okay.
and then, swagunitam. That's the square
So
of the
that
half.
is in chara in Vigatika.
Yes, that's right. Chara and vigatika, as usual. Yes, I have trivially substituted some definitions for some of the terms, but mathematically that is exactly the formula he gives. Right.
So stylistically, he's putting the finding the declination right at the end of the chapter. Is there any other reasons that he would put that last?
I have no idea. I call on Professor Balachandra Rao and his his colleagues. To, you're right. But no, that's a very good question. There is, to my mind, no reason that he could not have computed delta beforehand and then just used the known value of delta in some way for the hypotenuse calculation. But clearly he deliberately chose to put it there for some reason. And Professor Balachandra Rao here?
No, he had to leave.
Oh, right, yes.
So
Well,
I guess, is there more of a general trend to reduce down more technical, analytically correct formula from the Siddhantasiromani to these rules which rely on only one parameter, such as the chara, or the declination, or the like? Do we see that in other instances?
This is, in fact, the following rules in the Karanakutuhala Triprashna chapter, one for the declination itself and one for the latitude, as I have published in a couple of earlier papers, I think can be, the Bhaskara also gives very ingenious and imaginative and accurate formulas for them that are algebraic approximations. And seems to me that they naturally, intuitively break down from the trig approximation, or they are convertible from the trig approximations using exactly this sort of toolkit, using this sort of substitution, linearization, and then adjusting linear factors by a little empirical comparison.
Some anupata he has used somewhere,
Some
anupata.
Oh, I wish. Yeah, right. Some anupata as in.
That's what he does for many other arguments.
Yes, exactly.
So
I would like to discuss the comparison of how he approaches that, or if that sort of transformation in the Siddhantasiromani as opposed to Karanakutuhala. Yeah.
So I would like you to elaborate a little more on the third conclusion point.
Yes, here we go. Ding, 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 ding. Yes. The third conclusion point, this is our revered Gurudeva, Professor David Pingree, who said, made many good points about, who was the person who first got me into studying the commentary of Ekanath on the Karanakutuhala. But it has been mentioned, and I think perhaps too much has been made of it sometimes, that he suggested that the use of the particular style of the Karanakutuhala's sign table might suggest, because the radius is 120 and because of the adjustment of the values, and because Islamic sign table radii tend to be 60 or other sexagesimally neat values, that it might hint at the influence of Islamic astronomy on Bhaskara. That's always been definitely a tentative speculation, and I think this strongly suggests that it's not true. That we can explain the use of r equals 120 in strategies, transformation strategies like this, much more, naturally, independently.
I think there is also a comment by Professor Pingree in his monograph for the Wiesbaden that the Jyotpati indicates the influence of Islamic astronomy.
Yeah.
Could either you or Ikeyama say something on what is the...
Yes. I mean, certainly the Islamic astronomy, as in its mature form, is derived from Indian astronomy. The combination of the sign, it starts out with Greek chord functions, but it is mostly carried out using the Indian sine and cosine and verse sine functions. The sorts of trigonometric identities that we see in the Jyotpati are, they're similar in approach, you might say, or similar in interest to the sorts of trigonometric identities that Islamic mathematicians were interested in computing, but it doesn't seem to me that there is, that we need infer any relationship in that regard. Yeah, well, as Professor Ikeyama said, the Bhaskara900 is the first person, right? To, yeah, yes. No, I don't. Isn't Bhaskara900 the first person to do the sign addition formula? Hmm? Oh, I see, for the sign function. Remind me again, when is Abul Wafa? Islamicist.
And anyway, code version of that formula is Ptolemy's.
Oh,
yes,
the Prastaphyresis formula.
Chord version.
Right, a chord version of it. Yes, but yeah, I mean, I don't know, but clearly we see.
No, it's independent.
Yes, that seems most. I mean, Professor Pingree was very strongly a transmissionist. He was very interested in the transmission of math from one culture to another. But we don't have to. Many things are discovered independently. So.
Thank you very much.
Thank you.
We proceed to the next speaker.